Greetings to everyone. I, Dr. Jyoti Pillai, will be discussing about a type of data structure, that is linked list. Linked list is a dynamic, linear, non-primitive type of data structure. Why linked list is chosen? There are some limitations of arrays. Arrays are simple to understand and elements of an array are easily accessible, but arrays still have some limitations. Array elements are always stored in contiguous memory locations. Static memory location is needed, that is, memory allotment is required at the compile time. Prediction of size is another issue. Size of an array must be specified precisely at the beginning, which may be a difficult task in many practical situations. Once the size of array is defined, it cannot be increased or decreased during execution. A wastage of space may be there when array is used. Inefficient usage of storage space is there. If more memory spaces are allocated and that much memory space is not used by the array, then wastage of space results. Operations of array like insertion or deletion are pretty tedious as they require shift operations. To overcome all these limitations of the array, linked list can be used. There are various advantages of linked lists, as linked lists are dynamic in nature, which allocates the memory space dynamically when required. The unused space can be released in the situation where allocated space seems to be poor. Insertion and deletion operations can be easily implemented and are less time consuming in case of linked lists. Size of linked list can grow or shrink in size during the execution of the program. In linked lists, there is no need to know the size in advance as compared to arrays. Stacks and queues can be easily executed using arrays, but more easily it can be implemented using linked lists. Linked list provides flexibility in allowing items to be rearranged efficiently. What is a linked list? A linked list is a linear data structure that contains a sequence of elements called nodes, such that each node links to its next node in the sequence. Each node has two fields, data node and link node, and these nodes are randomly stored in the memory. Data field contains actual data stored at that particular address, and link contains address of the next node to point to the next node in the memory. Data part of each node stores the actual value of the data, whereas the link part of the node stores addresses of the next node. Linked lists are used to create trees and graphs. For example, here we can see 3 nodes. Each node is storing 3 data values 12, 20 and 29 at the data part of each node respectively. Head is pointing to the first node, link part of each node is pointing to the next node, and link part of the last node which terminates the list contains the null value. Array has got fixed memory spaces, that is, for example, in this case array has been allocated 6 memory spaces. ARR is an array, ARR 0 to ARR 4 has got 5 elements stored in its respective places. In the case of the linked list, these elements can be stored in the form of nodes, and the nodes are linked together through links or pointers. Head will be pointing to the first node and the last node will be containing null in its address part. There are basically 3 types of linked lists. The first one is singly linked list, second doubly linked list, and the third is the circular linked list. Singly linked list can be defined as a collection of ordered set of elements or nodes. Singly linked list can be traversed only in one direction in a sequential manner, as each node has only one link part. Each link part contains address of the next node. List cannot be traversed in the reverse direction therefore. Link part of the last node contains null value indicating the end of the list. For example, consider marks obtained by the student in 3 subjects which are stored in a linked list. The linked list will be consisting of 3 nodes. The arrow represents the links, data part of each node contains marks obtained by the student in different subjects, that is 23, 34 and 90 respectively. Last node in the list is identified by the null pointer in the address part of the last node. Head is pointing to the first node. The second type of linked list is doubly linked list. In doubly linked list, each node contains 3 fields. One is data part, which contains the data only. 2 other fields of the node are links or addresses, one pointing to the previous node and another to the next node in the sequence of nodes. The beginning and ending nodes, previous and next links respectively, point to some kind of terminator, typically a senatorial node or null, to facilitate traversal of the list. Here we have got a doubly linked list having 3 nodes. Each node is having 3 parts: previous part pointing to the previous node, data part containing the actual data value, next part pointing to the next node. 2 pointer variables, start and end. Start will be pointing to the first node, end will be pointing to the last node, making it capable to traverse in both the directions. The third type of the list is the circular linked list. In single linked list, every node points to its next node in the sequence and the last node points to null. But in the case of the circular linked list, as it is a sequence of elements in which every element has link to its next element and the last element has a link to the first element in the list. Circular linked list is similar to single linked list, except that the last node points back to the first node in the list. For example, in the diagram we can see that head is pointing to the first node, head is containing the address 1001. 1001 is the address of the first node. Address part of the first node or link part of the first node is pointing to the second node. Likewise, the address part of the last node is again containing the address 1001, indicating that it is containing the address of the first node. There are various operations which can be performed on the single linked list: creation of the linked list, traversing in the linked list, insertion into a linked list, deletion from a linked list, searching in a linked list, displaying the elements of the linked list. For creating a linked list, first of all we have to create a node of the linked list. So, let us discuss about the algorithm related to creation of a node. First of all, allocate memory to the header node using the malloc function. Then verify the memory location. If the header node is null, indicates that no memory is allocated, return the value. In step 3, we will be allocating next of the header as null, indicating the only element of that linked list and the node has been created, return h and the function. Now, for creation of the linked list, first of all see if there are n number of nodes in the initial linked list. Allocate n records one by one, read in the fields of the records, modify the links of the records so that the chain is formed or the linked list is formed. Algorithm for creation of the linked list: first of all create an empty list, allocate memory space to a variable h, a pointer variable h using malloc function. The next part, the address part of h is allocated as null, h is assigned to a temporary variable temp. Repeat following steps while user enters positive choice read x. Allocate the space for new node. A new pointer variable will be taken up representing a new node. Malloc function is used to allocate the space to the new node new, assign x value to new node's data part and link to null value. That is, data part of new node will be assigned as x, next part of the new node will be equal to temp of next or null. Link new node with the previous node also. Temp of next is equal to new, temp is equal to new, end while loop. This will be continued until all the nodes of the linked list has been created. Now, traversing the list. Once linked list has been constructed and head points to the first node of the list, first step is follow the pointers. Next, display the contents of the nodes as they are traversed or visited. Next, stop when the next pointer points to null value. Algorithm. Step 1, set PTR is equal to head or start. Step 2, if PTR is equal to null, write empty list. Go to the last step, step 6. Step 3, repeat steps 4 and 5 until pointer PTR is not equal to null. Step 4, print the value of the data, that is PTR data. Step 5, PTR will be incremented by PTR equal to PTR of next, end of the loop. Algorithm to set up for inserting a node in the linked list. First of all, we have to make a setup. First, set up empty list before implementing actual operations. Step 1, include all the header files to be used in the program. Step 2, declare all user defined functions which has to be used for the operation purpose. Step 3, define a node structure with 2 members, data and next parts. Step 4, define a node pointer head and set it to null. Step 5, implement the main method by displaying operations menu and make suitable function calls in the main method to perform user selected operations from the menu. In a single linked list, the insertion operations can be performed on 3 different ways. First, inserting at the beginning of the list. Only one next pointer needs to be modified in the case if the element has to be inserted at the beginning of the list. Next, head is made to point to the new node points to the previous first element. Second option for insertion operation is inserting at end of the list. 2 next pointers need to be modified. Last node now points to the new node and the new node points to null value. Third option is inserting at specific location in the list. 2 next pointers need to be modified, or you can say 2 next pointers of 2 different nodes have to be modified. Previous node now points to the new node and the new node points to the next node. Start with the insertion operation beginning of the list. Create a new node, then next part of the new node points to head of the linked list. Change the head to the newly added node. Algorithm can be step 1, if PTR is equal to null, write overflow condition and go to step 7. Step 2, set new node equal to PTR. Step 3, set PTR equal to PTR of next. Step 4, set new node data value to val. Step 5, set new node next to head, set head equal to new node and then exit out. For example, initial linked list will be having 4 nodes having values 4, 7, 8 and 10. The last node is containing the null value. The new node which is to be inserted at the beginning of the linked list is having the data value 1, having the link part as null. Now, when the new node is inserted into the linked list, in that case head now will be pointing to the new node. Head will be containing the address of the new node. Address part of the new node will be containing the address of the previous first node. Okay. That is, node having data value 1 will be containing the address of the node having the data value as 4. Insertion at the end of the list. Now, in the case of the linked list, traversing has to be done in a sequential manner. So, traverse the linked list till the end, till the pointer variable is null. Add a new node at the end of the list, change the next field of the last node to point to the new node and new node address to null value. Algorithm for inserting at the end of the list is step 1, if PTR is equal to null, write overflow, go to step 10. Step 2, set new node equal to PTR, then set PTR equal to PTR next, set new node data equal to val, set new node next is equal to null. Then set PTR equal to head, repeat steps 8 and 9 while PTR next is not equal to null until we have reached the end of the linked list. Set PTR equal to PTR next, set PTR next is equal to new node and finally exit out. Let us understand with an example. insertion at the end of the list. Again we will consider a linked list having 4 nodes containing 4 different values 4, 7, 8 and 10 and null value at the last node. Now, the new node has to be inserted at the end of the list. Head will be pointing to the first initial node. Now, the last node of the original linked list will be pointing to the new node having data value 1 and the new last node will be containing null value at its address part. The third condition for insertion operation, insertion at specified location of the list. Let us consider 2 nodes A and B, make a new node, point the next of A to the new node, point the next of new node to the node B. Algorithm for insertion at specific location of the list. Step 1, if PTR is equal to null, write out overflow. Whenever insertion operation has to be performed with any type of data structure, we have to first check for overflow condition, and if overflow condition arises, then go to step 11, that is exit out. Step 2, set new node equal to PTR, new node of data equal to val. Step 3, set temp is equal to head. Step 4, set I is equal to 0. Step 5, repeat steps 4 and 5 until I is less than LOC. Step 6, temp equal to temp next. If temp is equal to null, that is no node is present, display the message, go to step 11. Step 8 is I equal to I plus 1. Step 9, PTR of next is equal to temp of next, temp of next is equal to PTR. Step 10, set PTR equal to new node. Step 11, exit out. So, here discussion of insertion at a specified location using an example, taking the same original linked list having 4 elements 4, 7, 8 and 10. New node is having data value 1 with null as the in the address part. Now, when new node has to be inserted in between first and the second node, then address part of the first node will be pointing to the new node, address part of the new node will be pointing to the next initial node. The next operation which can be performed with the linked list is deletion. In the deletion operation also, we have to make adjustments to the different pointer variables. Like in insertion, deletion operation is also having 3 different options. First, deleting from beginning of the list, second, deleting from end of the list, third is deleting a specified node or a specific node. First, deletion from the beginning of the list. Make the head point to the next of the head. Free the pointer which was pointing to head node of the list. That is, when element has to be deleted from the first position of the linked list, then head has to point to the next second node and the first node will be freed out. Algorithm is step 1, if head is equal to null. Head is equal to null indicates that there are no elements in the linked list and the user is trying to delete an element from the linked list, which is not possible, which will give an error condition, that is display out underflow, go to last step, step 5. Step 2, set PTR is equal to head or start. Step 3, set head equal to head of next. Step 4, free pointer. Step 5, exit. Second option for deletion operation, deletion from end of the list. 2 scenarios in which a node is deleted from the end. First, when there is only one node in the list. When there is only one node in the list and that node is to be deleted, the list becomes empty. Second option is there are more than one node in the list. In that case, the pointer variables have to be adjusted. Algorithm for deletion from end of the list. Step 1, if start is equal to null, again indicates that it is an empty list, write over underflow and go to step 8. Step 2, set PTR equal to start. Step 3, repeat steps 4 and 5 while PTR next is not equal to null. Step 4, set previous of PTR equal to PTR. Step 5, set PTR equal to PTR next. Step 6, set pre PTR of next equal to null, and step 7, free PTR. Step 8, exit. Third option for deletion operation is deletion of a specific node from a specific position whose location value is given. Algorithm for deletion operation of a specific node is step 1, again checking for the underflow condition. If head is equal to null, write on underflow, go to step 11. Step 2, set temp equal to head. A temporary variable is taken which is assigned to the head value. Head is a pointer variable pointing to the first node. Step 3, set I equal to 0. Step 4, repeat steps 5 to 8 until I is less than location, LOC. LOC is the location of the specific node. Step 5, temp 1 equal to temp. Step 6, temp equal to temp next. Step 7, if temp is equal to null, write node not present, go to step 11. Step 8, I equal to I plus 1, end of the loop. Step 9, temp 1 of next equal to temp next. Step 10, free the temp variable. Step 11, exit. Now, the next operation which can be performed in the linked list is searching of any data value or any node in the single linked list. For that, the algorithm is step 1, set ptr equal to head or the start variable pointing to the first node of the linked list. Step 2, set I equal to 0. Step 3, if ptr is equal to null, write empty list and go to step 8. Step 4, repeat steps 5 to 7 until ptr is not equal to null. Step 5, if ptr data is equal to item, set LOC is equal to ptr, write I plus 1, that is the item has been found. Step 6 is I equal to I plus 1, else the continuation of the loop has to be done till we reach the end of the linked list. So, for that I is incremented by 1 in step 6. In step 7, ptr equal to ptr next. Step 8, exit. Now, the last operation which can be performed with the single linked list is display operation. Algorithm for displaying the value of a node of a linked list is step 1, check whether list is empty. First of all, we have to check whether the list is empty or not. If head is equal to null, indicates that it is empty, and if it is empty, then display out that list is empty and terminate the function for displaying the item. Step 3, if it is not empty, then define a node pointer temp and initialize with head. Step 4, keep displaying temp data until temp reaches to last null or last node, that is when the address part of the last node is reached to do null, indicates that the last node has been reached. Display temp data. Let us see the representation of a linked list in a memory. There are two ways to represent a linked list in memory. First method is static representation using array. Second way of representing linked list is using free memory space or dynamic representation using free pool of storage. First method, in static memory representation, two arrays of equal size are allocated and maintained. One array is used for storing data values of the nodes and other is used for links stored for the addresses of all the nodes. The second representation is dynamic representation. The efficient way of representing a linked list is using free pool of storage. In this method, there is a memory bank such as a collection of free memory spaces and a memory manager, that is a program in fact. During the creation of a linked list, whenever a node is required, the request is placed to the memory manager. The memory manager will then search the memory bank for the block requested and if found, grants the desired block to the caller. Also, there is another program called the garbage collector. It plays whenever a node is no more in use. It returns the unused node to the memory bank. Such a memory management is known as dynamic memory management. The dynamic representation of the linked list uses dynamic memory management policy. A list of available memory spaces whose pointer is stored in avail. For request of a node, the list avail is searched for the block of right size. If avail is null or if the block of desired size is not found, the memory manager will return a message accordingly, indicating that there is no free space. Suppose the block is found and let it be xy. Then the memory manager will return the pointer of xy to the caller in a temporary buffer, for example, q. The newly availed xy, that is the newly availed node xy, then can be inserted at any position in the linked list by changing the pointers of the concerned nodes, that is by adjusting the pointer variables to the different nodes. So, these were the two ways of representing the data. Now, let us see some of the applications of a linked list. Linked list can be used to implement several other common abstract data types or data structures, including lists, stacks, queues, associative arrays, S expressions likewise. Linked list lets us to insert elements at the beginning and at the end of the list or at a specified location of the list. But then there are some disadvantages of the linked list also. The memory is wasted as pointers require extra memory for storage. Every node of the linked list will be having two parts. One part is the data part and other is the address part or the pointer part, which points to the next node. That is, every link part or address part of the node will be containing the address of the next node. That means, we need that much pointers for storing address of the different nodes. For example, if there are 10 nodes of the linked list, we need 11 pointers for storing the addresses of different nodes. Address of the first node, address of the second node, address of the third node likewise. Access time is linear. No element can be accessed randomly, it has to access each node sequentially. Many basic operations such as obtaining the last node of the list, finding a node that contains a given datum or locating the place where a new node should be inserted may require iterating through most or all of the list elements. Reverse traversing is difficult in single linked list particularly. So, today we have discussed about linear linked list, its applications, its advantages and disadvantages, all the different operations which can be performed with single linked list. Thank you very much.